Okay. So if you remember, when we define the green strain, we define strain itself as the change in squared distance, right? Which we showed was d little x transpose dx plus d big X transpose dx, right? And then if you remember, we used this definition of the deformation gradient. And we substituted that into this guy so that we could get everything in terms of big X, right? D big X. And that's how we came up with the green strain. But what if we want to use a difference reference, right? And what if we want to get everything in terms of little x? Then we can solve this equation for d big X. That's F inverse d little x, right? And now we plug this in here. And we can get everything in terms of the little x's, right? So that'll be F inverse dx transpose F inverse dx. That's equal to just using the same thing, right? The transpose of a product is the transpose of each of the components with the order reversed, right? So then I'm going to have dx transpose F inverse transpose F inverse. So whenever I have minus transpose, that's inverse transpose. F inverse dx, right? We can write that. We can factor out the dx's. All right? So it looks close to what we had before, but a little bit different, right? And so we're gonna call this thing 2 little e. So then little e is 1/2 I minus F inverse, I'm sorry, this is inverse transpose, F inverse transpose, F inverse, and this thing is called the Eulerian strain or the Almansi strain. Again, the names green strain, Almansi, they come after the guys who, sort of first published this, right? So if the green strain is sort of like the engineering strain, right? It references back to the reference configuration, as apparent by the fact that we put everything in terms of big X's when we derived it, right? Then the Eulerian strain or the Almansi strain, we put everything in terms of little x, and little x is in the what configuration? The current or the deformed configuration, right? And so So this is a valid strain measure in the current configuration. All right. So let's just rewrite that here real quick. Now, if you remember, when we first drew our configurations, reference, deformed, the current, and we had, a vector x and a vector little x, right? And we wrote this as u, right? And u is a function of big X. So x1, x2, x3, right? But if we just drew that vector the other way, right? So if we just drew the vector u this direction, then now since it originates at little x, u would be a function of little x, right? x1, x2, x3. Right? So it's sort of the inverse mapping of u. Then just writing some vector addition again, we can say that little x, or rather, say that big X is equal to little x plus u, where I'm going to write clearly u as a function of little x. Just vector addition, right? Now I'm going to take the derivative of both sides of this with respect to little x. Well, this thing, remember we showed that f is partial little x, partial big X, right? So if that's true, then what is this guy? F inverse? Everybody see that? And then this is just the identity matrix, right? And then this, just like before that we had grad with respect to big X, now just for clarity, this is little x. We're going to take the gradient of little x of u, and of course we showed that that's really the transpose. Okay, so we have another identity, right? And so if we plug this guy back up here, then we'll have something that's basically looks the same as what we had for the Lagrangian strain. It's just now the gradients are in terms of the little x's. So or in additional notation, that guy. And so if we linearize this thing for small displacements, then we have that this guy, also the linear strain. Now it's identical to what we defined the linear strain before, but before we had big X in the denominator, right? Now we have little x, okay? But remember what we said, right? X is big X plus u of big X. And if the displacements are small, what we're saying is that approximately little x and big X are equivalent. And so the two finite strain measures, the Eulerian and the Lagrangian, they collapse to the same linear strain. Because we're saying for small displacements. So this is sort of the key thing, is that the linear strain makes no distinguishing between a reference and a deformed configuration. It's essentially the approximation of the linear strain is that the reference and the deformed configurations are the same.